Hello, welcome back to Larry's Classroom. We're going to talk about parallel circuits today. And let's start by thinking about what a parallel circuit is. I'm going to draw a circuit here. And this is going to be a 20-volt battery. We're going to have a resistor right here, and this will be R1 equal to 10 ohms. Another resistor here, we'll call this R2, also equal to 10 ohms. Now, what do we observe here? The applied voltage, we'll call this VA, voltage applied, it appears across R2. It also appears across R1. And you can look at these two circuits, these two halves of the circuit, independently. Basically, because of the low resistance of the wire, which we're going to call 0 ohms from here to here, and the same from here to here, we'll call that 0 ohms. Granted, a wire isn't perfectly 0 ohms, but it's so low for our purposes we can usually consider it to be 0 ohms. You can see that R2 is connected to this wire directly. At this point, we'll call this A, B, C, and D. We can see that the point C is basically the same point as point A, and point B here is basically the same point as point D. So this R2 is connected directly to the battery, and the applied voltage of 20 volts will appear with the same polarity as the battery directly across R2. We'll label these points here E and F, and we have the same situation. Because of the very, very low resistance of the wire, point E, the top on this drawing of R1, is connected to point A, which is the negative terminal of the battery. And point F is connected directly to point B, which is the positive terminal of the battery. So the battery voltage will appear directly across R1 with the same polarity as the battery, just the same as the battery voltage appeared across R2. And if we were to break the circuit, it doesn't change anything over there if we disconnect R1. And if we disconnect R2 the same way, it doesn't change anything over here related to R1. So essentially, R2 is directly connected to the battery, R1 is directly connected to the battery, and we call this a parallel connection. There are other ways to draw a parallel connection. I'm going to draw a little bit quick diagram here. We can have a multitude of components. Let's even put a light bulb in this thing here. These two resistors and this light bulb are connected in parallel. Let's put another resistor over here. We'll just label these R1, R2, R3, and we'll call this lamp 1. We'll call this the voltage applied, just like we had before. What we see here, no matter how many components we hook up this way, they're essentially just connected to the battery. So they're parallel connections. In kind of in the physical way we draw the circuit, you can see how they kind of look parallel, kind of like parallel lines, but that's not, wouldn't have to be so. If the diagram was drawn like this, and we had a resistor here and a resistor here, these would still be parallel connections, even though it looks like 90 degrees, because this circuit would change none if we put the resistor down there. So really the important consideration about a parallel connection, and if you have to analyze a circuit, they may be drawn where it's difficult to really see like it is here, but what we see here is, we'll call this point A and point B and point C and point D. We see that one end of the resistor, point A and C, is connected back here to, we'll call this point E, directly back to the battery. The other ends of both resistors, point B and point D, are connected back to this end of the battery, which we'll call point F. So really, what parallel connection really means is the ends of the component are connected back to the same point. Here, A and C are connected to the same point. B, D are connected to the same point. There's no way for, there's nothing in series. It's like, if we changed it, we did like this, and we took this into the resistor up here, now they're no longer parallel, because you'll see that this end of this resistor is connected to that end of that resistor. This end resistor is connected back to the battery. This end of this resistor is connected back to the negative side of the battery. So the two leads of these two components are not connected to the same place. In these parallel connections, every component has two leads, and they all connect back to the same place, the same power source, which is what makes it to a parallel connection. A very common parallel connection that we see in our world is the 120 volt AC supply in your home. And we'll just represent that this way as 120, and we'll go VAC to indicate an AC voltage. When you plug your toaster in, a toaster is basically just a resistor. We'll write toaster here. It connects back to 120 volt AC. Say you plugged in another appliance, a television set, TV set. When you plug it in, it connects back the same way through the power cord to the same points back at the supply in your lighting panel in your home. Maybe you have a desk lamp here. When you plug it in, it connects back to the same 120 volt supply. Maybe you have a microwave oven. When you plug it into the receptacle in the wall, it connects back to the same power source. So you can see each of these components, each of these devices connect directly back to the 120 volt AC. The toaster back to the 120 volt AC. The lamp back to 120 volt AC. The microwave. So in your home, when you plug devices into your receptacles, you're basically making parallel connections back to the lighting panel or service panel in your home where the power comes into your home. So that's a real common parallel circuit example that we see all the time in our homes, in our lives. We're talking a little more about what happens in a parallel circuit. We're going to draw another diagram. We're going to do a little bit more calculating with this one. Voltage applied equals 12 volts, and negative and positive. You've probably noticed already that the negative terminal of the battery symbol is shorter than the positive terminal. And we got a resistor out here. We'll call this R2, resistor number 2, and it's a 4 ohm resistor. We have another resistor here. We'll call this R1, resistor 1. And that's another, well, that's a 12 ohm resistor, 12 ohm. Now the first thing you'll notice, as we talked about, R2 is connected directly back to the power source. R1 is connected directly back to the power source. There's nothing all in between here, other than this very, very low resistance wire, which is the equivalent of the direct connection to the power source. So, as we talked about, being it's a parallel connection, we could calculate each branch of the circuit separately. And we'll call this I1, current through branch 1. And of course we have our Ohm's law, which is basically I is equal to voltage divided by resistance. So on this side we have I1 equals 12 volts divided by 4 ohms, which gives us 3 amps. So we got 3 amps in this branch. We'll connect this one back up. Doesn't change anything over there. We still have the 3 amps, and it's negative and positive. Now we'll figure out what we'll call this. Well, I want this to be I2. Excuse me, because it's with resistor 2. So we'll calculate I1 now in the branch containing resistor 1. And you see that it does go negative to positive. We'll use the same I equals voltage divided by resistance. So we'll say, now we're calculating I1, that was I2 that we did first, pardon my mistake there, is equal to the voltage applied again, because the voltage applied didn't change. The resistor is connected directly back to the source, the power supply, the battery here. Voltage applied divided by R1, which is 12 volts, divided by, we got 12 ohms. I'm going to write that over here. It's 12 ohms. Right, forms. So we end up again with 1 amp. So we have 1 amp here for I1. A couple things we'll notice here. The I3 and I1 combine in here in the same direction, so we'll call this the current in the battery. So what is IB? IB is going to equal the sum of this 3 amps and this 4 amps. So it's going to be I1 plus I2, which is basically 1 amp for I1, plus 3 amps for I2, which gives us 4 amps. So what I'm calling IB, the current in the battery, is equal to 4 amps. Now we've noticed here that R2 was a greater resistance than R1, or a lesser resistance. R2 was less resistance than R1. Well, being the resistance falls on the lower half of the fraction, as we decreased the resistance, the current went up. So here you can see that I2 was equal to 3 amps, and that was greater in value than I1. if we can make the opposite comparison, I1 is greater in resistance than R2, which makes the bottom bigger, the denominator fraction larger, which makes the current smaller. So you can see there's an inverse relationship. Less resistance, more current. Greater resistance, less current. Now the voltage source creates this 12 volts of potential difference. Potential difference, or we call it voltage. If we just read it with our own meter, that is our voltage that we will read. That potential difference does not move. It stays right there. And being this point is essentially the same point, you see it right here. So we'll put that right here, 12 volts. 12 volts, and we'll put the same polarity. That 12 volts doesn't move. It doesn't go through the circuit. The current travels through the circuit, but the voltage does not travel through the circuit. It is created by the power source, and it appears across anything that is connected to the power source. And by the same token, we'll see that same 12 volts over here across R1, because we're not moving voltage over here, we're connecting this resistors to the very same point, which is the battery. Now granted, as the battery wears out, that voltage can reduce, but it still doesn't move. Say after some time this goes to 11 volts. Well, that same thing happens over here. This goes to 11 volts, and this goes to 11 volts. So the potential difference didn't move. It changed because the battery became weaker, but the potential difference itself did not move to anywhere else. And we've also seen the sum of the current here, the actual current here, is equal to the sum of the current in each branch. So basically, the power source has to supply the current in all branches, so it's going to be greater than any of the individual branch currents. We have a branch current of 1 amp here, a branch current of 3 amps here, but we have a total current to our battery, which we call, well, we're calling it IB, the battery current, but it's greater, and it happens to be the sum of those two. I'm going to do one more quick little talk about that last diagram. Again, we've got the 12 volt supply. VA equals 12 volts. Negative, positive. Now we're going to put our R1 over here. Equals 12 ohms. And we're going to put our R2 over here. Equals 4 ohms. If we do the same calculation, we end up with our I1 equal to 3 or 1 amp. And here we have I2 equal to 3 amps. And again, our 12 volts appears here. And our 12 volts here. So this is basically the same circuit that we just looked at, though it's drawn in a different way, but still R2 is connected directly to the battery, and R1 is connected directly to the battery, so they're still in parallel because the two ends of the two resistors are connected to the same points, which makes them parallel, which happens to be the battery. So the way this is laid out, as long as the ends connect to the same points, it is still a parallel connection. And you can still calculate currents in each branch completely separately, other than the case when you overloaded the battery, which it would, if it was good design, that would not happen. The current in R2 would have had no impact on the current in R1 because the same voltage is going to be appearing across them two resistors because they are both connected directly to the battery. We're going to draw another circuit. We're going to do a little more calculating with that circuit. We're going to have again a 12-volt battery. 12 volts. We'll call that V applied, voltage applied. We're going to have a resistor here, and we're going to call this R1, which will equal to 6 ohms. And another resistor over here, we'll call this R2, which is equal to 12 ohms. Connect them all up here. We'll label these points here. I'm going to call this point A, point C, point B, point D, point E, point F. And we'll put the polarity signs. First thing we're going to notice here, like we talked about before, this is also a parallel circuit. R2 is connected directly back to the battery. R1 is connected directly back to the battery. What happens in this branch from C to D has no impact on what's happening in this branch from A to B, as long as the battery does not wear out. So we've talked about how the currents add up. So we're going to label, I'm going to call this I total. I total, which is going through the battery. And I'm just going to put it, up here where some I total through the battery. And it's going this direction. This is R1, so we'll call this I1 here. R2, we'll call this I2. We've got the directions consistent with the negative and positive polarities. And I think current, in the case of this type of circuit, we call this a node or a connection. I total equals I1 plus I2. And if there were more branches, we would do like we've been doing. We'd add it on up to IN for however many branch currents we have to deal with. In this case, we've only got 2 branch currents to deal with, which is basically I1 through resistor R1 and I2 through resistor R2. Now we're going to do a little new nomenclature here. We're going to put an arrow here. And we're going to call this IEF, which basically means current from point E to point F. And we're going to label this I1 a little differently. We're going to call it I A to B. Which means the current from point A to point B. And we're going to label this a little bit differently. Again, we're going to call this I C to D. So now we've labeled our currents based on what points or nodes they travel from. IE to F, went from point E to point F, which you can see by our older nomenclature that that's the same. So I E to F was equal to I total. Same current. Now our new nomenclature here, I A to B, that's the same thing as what we were calling I1 before. I'll relabel that as I1. IC to D is the same as what we called I2 before. I'll put the old label back up here. You can see that these are the same currents. Rather than label them by our specific subscript total 1, 2, we've labeled them by the nodes or points in the circuit that they travel. Here's from E to F, from A to B, from C to D. And of course, we're referring to all this in electron flow. So here we got a little total current flow. IT equals I1 plus I2. Well, we can also be in IE to F, the same as IT. We can say IEF, that current right there, is equal to I1, which is IA to B, plus I2, which is IC to D. Now let's calculate each of these. IE equals, that equals, well, we're going to calculate that with the total, so let's calculate IAB and ICD first. IAB is equal to, we'll put our current formula up here, which is voltage over resistance. That's our Ohm's law formula. And what we have here is IC to D, or IA to B, right here. Still the same 12 volt supplies. We're going to put the 12 volts across there. That's our current, our voltage. We're going to divide that by the resistance. In this case, we use the resistance of R1, which is 6 ohms. So that becomes 2 amps. So let's put that over here for A to B. 2 amps. Now we replace the symbol with the actual value. We're going to use the same formula to calculate I2. Again, it's 12 volts because the direct connection back to the battery. So the 12 volts is in the numerator of our fraction. And we're going to divide that by R2, which is 12 ohms. And this gives us 1 amp. So now IC to D we know is 1 amp, so let's replace that with 1 amp over here. We're just making a substitution of an actual value in for our variable value. Well, when we add 2 amps and 3 amps together, or 2 amps and 1 amp, we end up with 3 amps. So what we've determined by using our current total formula, that IE to F is equal to 3 amps. And basically, another way of looking at this is saying that this connection from the battery to the first component, we could call that the main line. It feeds everything out there. See, this section, you see it feeds resistor 1, it also feeds resistor 2. So we can say that the main line current, or sometimes you might call it the feeder, is equal to the sum of the branch currents. So we calculate a mainline current by adding up the branch currents that we calculated using Ohm's law. Now, let's see, what do I want to do next? Okay. And in your home, say you had a TV set that used, we'll say that thing uses 4 amps. Maybe you have a toaster that uses, we'll say 6 amps. and maybe a microwave oven that uses, let's say, 10 amps. These could each be considered branches. When they were all running, we would have 10 plus 6, 60, we'd have 20 amps being fed off the main line, or the lines coming into the top of your panel in your home, and each of these might be going out through a separate circuit breaker, or if they were all plugged into the same circuit breaker, the wire feeding the first outlet would be carrying that 20 amps. Say the first outlet was the TV set. The wire going to that first outlet, that's a diagram for an outlet, you see the two slots, would be carrying 20 amps. And we have a TV set plugged in here. Now after that, we're only carrying these other two, 10 and 6. So now we've only got 16 amps because the TV set took 4 amps. We'll write that 4 amp down here. And maybe the next circuit is where the microwave's plugged in. And that thing was 10 amps. And then we have one more receptacle. So, okay, we had 20 amps. We took 4 off for the TV set. That left 16 amps being in the wire going to the next receptacle. I'm going to first, second, third receptacle. So that 16 amps, we fed 10 out to the microwave. What we have left here is 6 amps. And that is, into that last piece is plugged in the toaster, which is a 6 amp device. So this kind of shows you how the current's split up. The first one, we might call this the main line. Main line, because it feeds power to everything else down there. The second one could be the main line for these two, because it feeds power to both of those, but it's just another extension of the power source. But you notice they're all in parallel, because we'll say that the top wire goes to the left one here, and that the bottom wire goes to the right one. Kind of hard to draw this, but all of these left slots in my drawing here are connected to this top wire that I've drawn, the top conductor. All of these right slots were connected to the lower one. So we created a big parallel circuit there, and we have shown kind of how the main line and each section of wire further past each power consumer, the current becomes less and less. Or if you went the other way, you start with 6, then you add the 10, you add the 4, and it would add up to the full 20. So we've done a little bit of more talk about parallel circuits. We've seen that the main feeder has the sum of all the branch feeders. So we're going to do a couple more examples here. We'll say we have this circuit here, 120 volts source, and we got a 40 ohm resistor, and we have a 60 ohm resistor, and we have another 30 ohm resistor. And we'll call this R1, R2, R3. So we want to figure out each of these currents and determine how much is being drawn off the source. Well, again, we have I equals voltage divided by resistance. So here the 120 volts appears across each of these branches. There's nothing to impede it. There's a direct wire back to the power source from each of these parallel branches. So here we have 120 volts over 40 ohms, and that gives us 3 amps. Here we have the same 120 volts, and this is using this current formula from Ohm's law. We have 60 ohms, which gives us 2 amps. And here in the last case, we still have the 120 volts. We have a 30 ohm resistor, so we have 120 volts divided by 30 ohms, and that gives us 4 amps. So if we want to know the total amperage coming from that power source, we can do this. We can say I total equals 3 amps, which we got from there, plus 2 amps, which we got from right there, plus 4 amps, which we got from right there. If we add that up, 3 plus 2 is 5, so we get 9 amps. So there's one way we can calculate. If we know the branch currents from each parallel branch, we can determine how much current is being drawn off the power source. All right, we'll do another example where we solve some things based on this stuff. We again have a 120 volt power source. And we got a branch which is some load which will represent by a resistor, and we know that we have 4 amps here on that, drawn through that first thing, that first branch. Second branch, we have another load. We'll call this I1, we'll call this I2. I2 is not given to us, but we are given that the total is 10 amps. Coming from the source. I'm going to put polarities on these so that we got directions similar. Well, what is I2? Well, we'll go back to our current total formula that we use. IT equals I1 plus I2. Well, what do we have? We have IT. So, and it was given to us as 10 amps, so we'll like 10 amps equals I1, which was given to us, 4 amps, plus I2 that we do not know. But we have here an equation with one single variable, so with a single equation, single variable, we should be able to find the value of that variable. How are we going to do that? We're going to subtract the 4 amps from both sides in order to keep this equation balanced. And our goal is to get all the no-ones, which are the 10 amps and the 4 amps, on one side of the equal sign with only a single variable on the other side. Well, 10 amps minus 4 amps leaves us 6 amps. And 4 amps minus 4 amps is 0 amps, so we don't even need to write in there, but we still have I2. So by using the branch, or the parallel branch current total formula, we have been able to solve for what I2 is. We didn't know it before, but now we know that I2 equals 6 amps. And this is just another example of using this I total formula. We're going to do another one here, a little bit differently, or pretty similar, but nonetheless. We have a voltage source, VA, and we don't even know the value of it, but we do know it's negative and positive. And then we have 3 resistors. We don't know the values of these resistors either, but we're given some other information. So we have a parallel circuit, a voltage source with 3 loads. We'll call them R1, R2, and R3. We don't know the values of the resistors. We can see that they're all connected directly back to the voltage source, which makes them a parallel, three branches of a parallel circuit. But we're given currents, 0.2 amps here, 400 milliamps here, 500 microamps here. Now we can add those up using this, we'll call this I1, I2, I3, and we'll put some arrows to indicate the direction. We can use that, we can find the current from the source using the IT, I total equals I1 plus I2 plus I3. Now, when we're going to add things together, you've probably heard many times you can't add apples and oranges. Well, you can't add amps and microamps. You can't add milliamps and microamps, or microamps and amps. So we have to put these so that they are in the same terms. So let's start with I1. I1 equals 0.2 amps. But the equivalent of that, let's change it to milliamps, is equal to, that's equal to 200 milliamps. And you remember that a milliamp equals 1 times 10 to the minus third amps. So if we have this in milliamps, the decimal point would be here, but the minus 3 would say, move it like there to convert it to amps, so it would be 0.2 amps. Another way to look at it, if you want to convert amps to milliamps, multiply by 1,000. Now when we went the other way, to go from milliamps to amps, we're moving our decimal place this way, we were dividing by 1,000. But multiply by 1,000 is move decimal 3 places to the left, or to the right. Each time you move the decimal place 1 to the right, you made the number 10 times larger, but you made the unit 10 times smaller, and that's why they're still equal. I2, it's already in milliamps, so let's just leave that at 400 milliamps. I3, 500 microamps. Well, that's a microamp equals 1 times 10 to the minus 6 amps, or a microamp is equal to 1 times 10 to the minus third milliamps. So might be kind of hard to see. I have this little M for micro and this little mu that looks like kind of a stylized U for micro, and the M for milli. So to convert microamps to milliamps, we have to divide by 1,000. So 500 microamps equals 0.5 milliamps. And we got that by moving this decimal places 3 places to the left too, to make the number smaller. When we did that, we made the number smaller, but we made the unit larger. A milliamp is a larger unit than a microamp. So I3, we had 500 microamps, which is equal to 0.5 milliamps. Now if we add these all together, 200 plus 400 plus 0.5, this, we're using our IT, we're gonna write that down here. IT equals I1 plus I2 plus I3. So we've calculated these. We're going to substitute for I1 the 200 milliamps. We're going to substitute for I2 the 400 milliamps. And we're going to substitute for I3 the 0.5 milliamps. Well, 200 plus 400 is 600 plus another 0.5, that equals 600.5 milliamps. So what we demonstrated here is that this parallel total current thing works with these smaller values too, but we had to convert them all into the same unit to add them up. You know, you can't add apples and oranges, you can't add milliamps and amps. And what we find by totaling these up, we have here 600.5 milliamps total coming off, being supplied by our power source. We could have converted them all to amps, we could have converted them all to microamps. We chose to, in this case, we used the kind of the middle of the road unit, milliamps. By getting them all in the same units and adding them up, our answer is in that same number, in that same units. Anyway, I think we're going to call that good for today. And remember to like and subscribe. And until the next time, keep on learning.